Thank you, Chris. Thank you, everyone, for allowing me to speak with you here today. I'll go through some slides and talk about nuclear energy, a little bit about the current state of nuclear energy, but a lot about the state of the next generation of nuclear energy. And I don't know what your typical format is. I'm happy to take questions throughout the presentation, so you don't feel you have to hold them till the end with me. Before I begin, actually, I'll talk a little bit about the Nuclear Energy Institute. So we're the trade association for the nuclear energy industry. That means that our members are nuclear energy companies. They're the utilities that own and operate nuclear, the companies that design and develop the technology, supply the components and other things to nuclear power plants. And our role really is to be advocates of the nuclear energy industry, both in terms of policy in front of Congress and state and federal administrations, but also in front of the regulator, and also to provide accurate information to help educate the public and media on all things nuclear. So I'll go into the current state of nuclear energy. We have almost 100 nuclear reactors in operation today. Those reactors are typically 1,000 megawatts in size, so they're very large. And that nuclear energy represents just less than 20% of the total electricity generated in the United States, but it accounts for almost 50% of the zero carbon or clean air energy in the United States. And the nuclear fleet has been operating since the 1960s. Just to also mention that these nuclear power plants, many have been in operation about 40 years. They have approval from the Nuclear Regulatory Commission to operate to 60 years. Many of them almost all of them are going to apply for application extensions to 80 years. And at the current time, there's nothing in engineering space that indicates it would prevent them from operating to 100 years safely. So when we start to look at advanced nuclear technologies, the next generation of reactors, we first start with the companies that are developing the technology. There's a list here. These are just members of NEI that are developing advanced reactor designs. There are probably more than 60 out there in the United States, many more worldwide. These represent the ones that are more mature and closer to commercialization. Even out of these, there's a subset that are further ahead than others. What you might notice is that there's a mixture of companies here. You'll notice that there are some you've heard of before: Westinghouse, General Electric, Hitachi. Those BWXT have been in the business for a very long time, since the dawn of nuclear energy in the United States, and they're well-established nuclear developer companies. There are others that you've likely heard of that are more new to the space: NuScale, X-Energy, TerraPower. They have quickly matured in their development, engineering, and capabilities. But they're relatively newcomers into the nuclear space. And then there'll be companies that you probably have never heard of before: Last Energy, NuGen, Radiant, others. And they're earlier in their progression to developing the technologies, but nonetheless, they're making significant headway. The thing that's common with all of these companies is that they see nuclear energy as vital to a clean and sustainable world. So a lot of them look at nuclear energy as vital to clean electricity and other energy production, but also many of them look and recognize that energy is a foundation of a sustainable living environment, and that there are many parts of the world that don't have access to clean, stable electricity. And so some of them are developing designs specifically intended to be brought to other parts of the world. When we look at the different technologies, there's a couple of ways to look at them, because all of those different companies all have different designs. There's some similarities and there's some differences between all of them. So there's two main ways to look at it, to group the technologies. One is by size. The other is by the material that's used to cool the reactor. So first, in looking at size, I mentioned today's reactors are 1,000 megawatts in size. We have two types of sizes for advanced reactors. We have small modular reactors. These are 300 megawatts for the reactor size or smaller. And they're modular because you can put multiple together to make bigger units. One example is the NuScale shown here. Its reactor is 77 megawatts. It can come in packs of 4, 6, 8, 10, or 12, so that you can customize the amount of power you need for that particular plant. The other size that we look at is called microreactors. These are 1 to 10 megawatts in size. They're not really intended for grid scale applications like we see in the lower 48, or even large amounts of industrial process heat. They're more intended for replacements of large diesel generators. This is perfect for remote applications or anywhere else you need to power a small microgrid or small amounts of power. The other way to group the different types of technologies is by the material that cools the reactor. So today, the reactors in operation in the United States are all cooled by water. We have water-cooled advanced reactors. NuScale is an example there. And then the others shown here, X-Energy, TerraPower, and Terrestrial, are all cooled by something other than water. X-Energy is an example of a gas-cooled reactor. That gas is helium. The TerraPower is an example of a liquid metal-cooled reactor. They happen to be using liquid sodium. And then the Terrestrial reactor is cooled by molten salt, and there are many, many different types of those. Now, within those, there are some technological differences, certainly where it comes into play of engineering and materials and operations. There are differences. But if you zoom out to the macro picture, there's a lot of similarities among all of these advanced reactors, and I'll go into a lot of discussion on that. The one major difference between water-cooled reactors and reactors not cooled by water is the temperature at which they can operate. The non-water-cooled reactors can operate at much higher temperatures, and this is going to be an advantage when we start to look at non-electrical uses of advanced reactors. This is another picture of many more of those designs plotted on it's actually the y-axis is a log chart. But it shows the different coolant temperatures and the different sizes, and it shows where many of these designs fall along those parameters. And the main purpose here is to show that we have a broad set of technologies that are being developed. And so I talked about the current reactors in operations are 1,000 megawatts. It's that one product for the market. And this is developing what we're calling a portfolio of advanced nuclear technologies, really designed to meet a diverse set of market and customer needs. And so what's really, really exciting about the next generation nuclear is that we're bringing nuclear technology into markets and to customers that never could before have access to nuclear energy. 1,000 megawatts might be too expensive for some, might have too much power for others. It might not produce the heat at the temperatures that they need. It might not be flexible enough to integrate with renewables or do other things. And so this is really bringing nuclear energy to many more applications and customers. And to talk about what those things are, we talked about the size aspect of it. On the energy products, we look at three main energy products. We looked at electricity, which is the traditional product that nuclear energy produces. But there's also heat directly, and there is hydrogen. So a unique thing about nuclear energy is it is the only clean energy source that produces heat that can be used directly. All the others produce electricity, which would have to be converted into heat. And so when it comes to decarbonizing other sectors, this is a real benefit. So if you think about the decarbonization of the entire economy, and especially the energy area, most focus is on electricity. But electricity generation is only about 1/3 of the total carbon emissions from all energy sources. The other 2/3 come from transportation, which some of it we can electrify. But if you electrify, you're going to need more electricity generation. and the other comes from industrial processes, and that's represented by a lot of these uses. So we'll talk a little bit more about many of those industrial processes, but they use heat directly. And so this is something that nuclear energy can help to decarbonize. Now, there's also a lot of discussion about hydrogen. And hydrogen can be used for generating electricity, used to generate heat, and that heat used in a clean way as long as the hydrogen was produced by a clean energy source. But hydrogen itself has to be produced, and it has to be produced by using energy. And so that's just something to keep in mind. I want to talk just a little bit more about the microreactors that I mentioned earlier and talk about some of the markets that they can be used in, because this is one of the most innovative technologies of the advanced reactors in terms of what it can do. There are two types of microreactors. We call them stationary or fixed, and then we call them mobile or transportable. The stationary are intended to be at the location their entire lifetime. They're not going to be operated for a time, moved to another location, and operated again. That's what the mobile are intended to do. You'll move them to a location, you'll operate them for however long you need them. When you don't need it any longer, you turn it off. You wait to be able to let it cool off, and then you can transport it to a new location and then turn it on and operate it again at that new location. So there are different market applications for those. The stationary are really well positioned to serve remote markets. Alaska and the Arctic in Canada are two areas where most of the attention has been given to using microreactors. And the reason is that the cost of power in some of those Arctic areas is $1 a kilowatt hour compared to about 6 cents that most of us pay. And so for them, now they actually in Alaska, they do have a government-supported price subsidy for those very high cost places. And so that does help to reduce their costs, but they're still paying maybe 60 cents. And so it's a lot more. And so for those areas, especially because they need a lot of heat in the winter, it can be questions between do I heat the home or do I eat type of prospect. And so the microreactors are coming in at costs that are much lower than that. Generally we're looking at the 30 cents 30 cents. So it's about a third or a half of what currently is produced. And a lot of that cost is in the transportation of diesel fuel to those areas. So there are other microreactor applications for the stationary. We can use them for microgrids in more closer to populated areas. Mining is a great example. And then the Department of Defense is very interested in microreactors on the stationary side because they need resilience and they need protection against cyber and other threats. On the mobile side, they're interested because they need to have reliable power to be deployed for their operations. The other thing is humanitarian and disaster relief. Now, in the Pacific, our Navy responds to disaster relief quite frequently, and so they need power to be able to quickly restore life and habitability in those areas. But there are other applications for disaster relief, and I have seen bills in Congress that are promoting the use of microreactors, even here by FEMA, to be able to respond to disasters in the U.S. Moving on to more discussion on those non-electric uses, those industrial heat processes. This is a chart that shows the different types of industrial processes by temperature range, and then on the left you can see the temperatures at which those different advanced reactor technologies can achieve. So you'll see the water-cooled are not able to achieve temperatures as high as the other types of reactors, but still they're quite useful in even pulp and paper production, desalination. You can even use it for hydrogen production at low temperatures. When you get into the higher temperatures, that's when you really get into decarbonizing many other sectors. So ammonia is a very important chemical in society, and so we can help to decarbonize that. You can also do petrochemicals and also produce hydrogen. Hydrogen produced at high temperatures is actually much lower cost than producing only with electrolysis. And so this heat-assisted electrolysis is going to be able to produce hydrogen at a much lower cost. There are other applications not listed here. This is just a representative list. One of the hardest things to decarbonize industrial heat process is metal refining because they operate at such high temperatures. One of the things that people are starting to discuss is that the heat that's taking off of advanced reactors, because it's a very dry heat, is very easy to increase its temperature through electric heaters that boost the temperature up a little bit higher. So there are opportunities to still use nuclear energy directly, nuclear heat directly, even at temperatures above what are shown here. Looking at now we're going to focus more on the electricity sector. And as we look at what is needed to decarbonize the electricity sector, we have first a chart of many utilities. Almost all the utilities in the U.S. at this point have made carbon reduction pledges. And each pledge looks a little bit different, but most of them are reaching zero or close to zero carbon emissions by 2050. And so you can see here what that would do with the cumulative carbon emissions from electric operations between 2020 and 2050. It's a very significant decrease. But what that means is that they're going to have to replace their carbon emitting generation sources with non-carbon emitting generating sources. And so one of the things that the utilities started to ask themselves is, what is the right generation mix to decarbonize our electric operations, our electric generation? And electricity companies, when they started to ask this question, they recognized they have a duty to serve, which means that they are required to produce reliable and affordable power. And so now they have to have clean, reliable, and affordable, and they started asking themselves, what is the right generation mix from a planning standpoint? And there's been many studies out there, and most all of them conclude that we need nuclear, and we need more than we have today. This study is my favorite study from Vibrant Clean Energy, and the reason it's my favorite study is because it's the only one I know of that actually matches supply of electricity and demand or use of electricity on an hour-by-hour basis and in a geographic basis. So they actually took, I think it's 3 kilometers by 3 kilometer grid of the entire United States and modeled where the electricity was being used. And actually, as they ran the model, it actually put locations exactly where generation sources needed to be in order to have the most optimal supply and demand balance. And so when they ran that model, the model concluded that we need a lot more nuclear energy than we have today. So I mentioned we have 20% today. This predicts we need 43%. The amount of electricity that we need is increasing over time by 2050. And so that represents 300 gigawatts of additional nuclear. I mentioned earlier we have about 100 gigawatts of nuclear, this is by capacity, on the grid today. So we need 3 times more than what we currently have today. The rest would be shared by wind and solar, and there would be some battery storage to complement that as well. The model said, well, 300 gigawatt, or the modelers said that 300 gigawatts of new nuclear is a lot, and maybe we don't have confidence we could build all 300 gigawatts because the regulator may not be able to keep up with the casework. The supply chain may not be responsive. We may not find all the workers we need to do this. And so what if we model an artificial constraint that nuclear can only deploy 60 gigawatts? And so they ran the model again with that constraint in it, and it found other generating sources to fill the gaps. And this model, it mostly picked wind and solar with additional battery backup. Now, between those two scenarios, both of them achieve a 95% reduction in carbon emissions. Both of them result in acceptable reliability on the grid. The difference was in the cost. And what it found is that a grid without the optimal amount of nuclear was going to cost $500 billion more. And that $500 billion more has to be picked up by people that pay their electric bills. And so one of the reasons why I like studies like this, not because I'm an advocate for nuclear and it says we need a lot of nuclear, but because it actually looks at the question in what I think is the right way, which is what's the total cost of the system? Because that's the cost that we have to pay in our electric bills. A lot of people look at what's called a levelized cost of electricity, and that basically averages all the energy that it's going to generate over the cost that it's going to incur and says, well, here's your average cost. And by doing that, you miss a lot of the features about matching supply and demand, hour by hour, geographic, and a lot of other things are missed. And so you could come up with the wrong answers if you look at the simplified models rather than a more detailed and sophisticated model. So what are the benefits of nuclear energy? Well, all nuclear energy shares a couple of benefits. One is long-term price stability. So we're a very high upfront capital cost technology, but we have very low fuel and operating costs. So what that means is we don't have a lot of fuel cost variability that impacts the cost to the customers. The other thing we have is the reliable dispatchable operations, 24 hours a day, 7 days a week, 365 days a year. Very high capacity factors. That means the total amount of energy produced over the maximum theoretical amount of energy produced if it never stops running. And the reason that it's 92%, that accounts for refuelings. So the current reactors refuel every 1.5 to 2 years for about 30 days, and that's what brings it down to 92%. Some advanced reactors are looking at having 10 or 20-year fuel cycles, and so those capacity factors and reliability could be much, much higher. There's also inefficient use of transmission, so a lot of those studies don't actually account for what it's going to take to connect generation to the grid, the cost of transmission, the building of transmission. And so nuclear sources have a benefit in that they're small, compact, a lot of energy in one small location. And so the amount of transmission lines you need to connect it to the grid are much, much less. And that shows up in terms of land utilization. And I talked a little bit about environmentally friendly before. It's not just the lowest, not just zero carbon emissions during operations, but total carbon footprint, one of the lowest. It's tied for the lowest with wind. Now, what advanced reactors do, two things that are a little bit unique for advanced reactors. They're building in flexibility. So the nuclear reactors of old didn't have to think about being flexible and integrating with renewables that would vary over the time of day. And now that we know that that's a thing, so now we can develop advanced reactors that can better integrate with renewables. And they can do it a couple of ways. It certainly could fluctuate in its power output throughout the day. A better way of doing it is actually called a hybrid energy system. And so when it doesn't need the electricity, the grid doesn't need its electricity, it would actually shift over and either produce heat for some process, or it would produce hydrogen. There are some designs that are looking at heat storage, which is much more efficient than battery storage in terms of cost. So that's how it's looking to integrate. And then the other thing is black start capability. That means if the entire grid goes down, the advanced reactors can start up. They don't have to wait for the grid to come back before they can start up. So they can actually be the source that helps the grid start back up. And that's related to independent operation from the grid, in that if you have especially if you have mission critical activities and the grid goes down, these can continue to operate to power your mission critical activities. The reason that that's possible, I'm going to get into safety features a little bit later, is because today's current reactors, the safety profile requires power from off-site to maintain safety. And these advanced reactors are being designed with safety features that no longer require that off-site power. And so that's why they have this new feature. The advanced reactors, there's a lot of different definitions for advanced reactors. Now, the best definition is that an advanced reactor, it has some improvement over the current nuclear reactors in operation today. That improvement could be in economics, it could be in fuel utilization, lower waste yields, it could be enhanced safety, it could be more flexible operations or applications that aren't available today. Could be many of those things. But one of the things that a lot of them share in common is the economic and cost, some advantages there. So it's a little bit counterintuitive. What the industry went to are ever larger nuclear reactors because you get economies of size. And so that led us from the first nuclear reactors were not 1,000 megawatts, they were a couple hundred megawatts, and then they grew to 1,000 megawatts. Now today, one of the reasons we're driven to smaller reactors is actually because the market is signaling they don't need 1,000 megawatts or want 1,000 megawatts at a time right now. They want smaller amounts. So that drove us to developing smaller. But what we found is as you shrank them, the safety characteristics actually started to benefit us. So you have a smaller amount of radioactive material to worry about. That helps on the safety side. You have smaller amounts of what's called decay heat. That's heat that continues even after you've shut down. So that helps on the safety side. The other thing is that because of those things, we can now use more of the natural phenomenon to keep the reactor safe. And what are those things? That's natural circulation, that's gravity, things that nature does and always works. Because the safety that we had to add into reactors as they got larger and larger were more backup systems, more complicated systems to be a backup. And so that complexity has a cost associated with it. Counter to that, as you make them simpler, there's a cost savings, and that actually is bigger than the reduced economies of size. So we call that economies of simplicity, economies of safety, economies of smallness. There's different names that we call it. The other thing about advanced reactors, because of the smaller size, we can now do more of the construction in factories. That has advantages because you have better control over the quality in factories, but you can also do more parallel work in factories. So time is money, and the faster we can construct nuclear power plants, the cheaper they're going to be. So that helps. The other thing we found is that there's a lot of complexity and cost associated with what's termed stick building it on site. And so if you think about it like building a house, in the old days, they'd deliver a bunch of lumber, you'd cut it on site, and then you'd try to put it together, and that's stick built. Today, most homes are built with modules, and those modules are basically things that are pre-measured. They're in standard forms because you know you're going to build a lot of the same homes to the same spec. And then you deliver them, and you basically just assemble them, and they go up much faster than they did in the past. So those things help to drive the economics. When we look at safety, because I said economics and safety are not opposed to each other, in fact they're complementary. So what is the safety of advanced reactors? Well, today the nuclear industry is one of the safest industries in the entire world. And that's not well known, but it's true. And if you look at the number of accidents and deaths and things like that, it's one of the lowest industries in the world. So why is that the case? Well, there's three pillars, I think, that build upon nuclear safety. The first is that the reactors are built tough. They're built to very high standards. When you think about any particular type of event that might happen, whether it's an earthquake or a tsunami or anything like that, these are built to the highest standards to try and be able to withstand those. The other is that we have a strong and independent regulator, the Nuclear Regulatory Commission. They're very strict. Many people in the world call them the gold standard of nuclear regulators. And they're very well respected, and so they help to hold the industry to very high standards. And then the third component is in our operations. So over the years, we have learned to operate with higher levels of performance. And what we find is the better you maintain and operate a nuclear power plant, the more safe it is. And so those three things are sort of our bedrock of safety. We're adding for advanced reactors to that. So we have a lot of experience about what could go wrong and how it could go wrong at a nuclear power plant. And so we're looking at that in the design space and saying, well, how do we make a design that couldn't go wrong? And so we're designing those accidents out. That's one way we're looking at it. I talked earlier about the natural forces, gravity, natural circulation that help to make it safer. And then even within that, if there are even some accidents that are still possible, what we're doing is designing them so that you have much more time to be able to respond. And that gives people more time to be able to respond. A lot of reactors are being developed so that you don't need power or human action or additional water to be able to cool these, so that they're basically able to go indefinitely without having to have a concern about a fuel melt. So we also get a question about the waste, and we call it used fuel, but other people call it waste. And a lot of people focus on Yucca Mountain and point to it and say, well, the industry doesn't know what to do with the waste. And I think the truth, it couldn't be further than the truth. And so I think it's important to step back and look at it. And all technologies have a waste stream, and every technology has to do what I think are the same three things to address their waste. First, they have to be able to handle it safely. And so what the nuclear industry has done for decades now is manage our nuclear used fuel safely. We can deal with it, we can store it in a pool for a while. Eventually we move it into what are called dry storage canisters. So these are steel and concrete that protect the public and people from the used fuel. We can do that because used fuel is very, very small. And so if you take all the used fuel in the United States and put it all together, so that's about 20% of our electricity over about 40 years, it would fill the size of a football field. So it's very small. The other is that it's a solid. So if you looked at a new fuel assembly and a used fuel assembly, you couldn't tell the difference by your visual eye. One has radioactivity, the other doesn't, so you could measure it and tell the difference. But it's a solid form. And so it's very easy to protect people from waste that is a solid form in a very small, compact space. And our Nuclear Regulatory Commission independently verifies that. And that we can store it for a very long time, hundreds of years, safely in those methods. The second thing you have to be able to do with your waste stream is to be able to pay for it. And the nuclear industry is unique in that from the beginning of operations, we set aside and continue to set aside money to be able to pay for the final disposal, well, the management and final disposal of used fuel, and not just used fuel, but also the decommissioning of the nuclear reactor as well. Today we have about $40 billion saved in the U.S. Treasury account to be able to pay for the disposal of used fuel. The third thing you have to have is a place to put the final waste form. And so in the United States, Yucca Mountain by law has been declared as the place to store it. Now there are people in Congress, some want to continue with Yucca Mountain, others want to find a new site using a consent-based process. And the way I look at it, I actually think about it as this is a 10,000, 100,000 year decision. And so it's worth taking a few extra years to come to the right decision, because there's no urgency to move this used fuel into a repository. We can store it safely for a very long time, so it's better to get this decision right for all of us to talk about it and come to some alignment on what it is. The other thing is, the reason we call it used nuclear fuel, we only use about 5% of the energy from the fuel. The other 95% of the energy could be recycled and then reused again. Now today, it's just not economically viable to recycle in the United States, but someday it could be, especially as the price of uranium goes up. And so being able to preserve that as an option is really, really important. Going into the technologies, I'm going to maybe just run through a quick few of these. These are looking at the designs of different types of technologies. The first one's a light water, small modular reactor technology. This is NuScale. NuScale's been working on their design for over 10 years now. They actually have design approval from the Nuclear Regulatory Commission. They are going for what's called a power uprate. So their design was approved at 50 megawatts. They found some design enhancements and some engineering fixes, or not fixes, but engineering solutions to help improve the economics and performance. They can actually get basically the same reactor up to 77 megawatts with just a few key design changes. And so they're going to the NRC to get that power uprate approved. They have a project with UAMPS, which is Utah Associated Municipal Power System, for their first project to be in operation by 2030. That's going to be located at the Idaho National Laboratory. The next technology is called TerraPower. They're actually collaborating with GE Hitachi on their design. Their design is called the Natrium. TerraPower actually has multiple designs. So this Natrium is the one that they're moving forward first. The Natrium is a liquid sodium fast reactor, and this is one that has one of those molten salt thermal energy systems with it. They're partnered with PacifiCorp. Their location is in Kemmerer, Wyoming. Their project is to replace a coal generating asset with a nuclear power plant. It won't be exactly it won't be on the exact location where the coal plant was. It's going to be a little bit away from it, just because they didn't want to deal with the environmental issues of a coal plant. So they're going to be close. They're going to still be able to use some of the infrastructure, like the transmission and that sort of thing. Now, some of these reactors that I'm going to talk about, the non-water-cooled one, they use a form of fuel called HALEU. This is in the enrichment. So enriched fuel for water reactors is up to 5% by weight of uranium-235. That's the isotope that's used for fissioning. HALEU is enriched to 20% by weight of uranium-235. We don't currently have a commercial supply for HALEU. The only place that can even manufacture it today is in Russia, and so that's not a source that we are going to use. But the Department of Energy is working with a company called Centrus, who has done enrichment in the United States in the past, to do a pilot program to demonstrate that it can be done. There are other companies that could do it in the United States. They need more signals from the industry that form an order book for them to make that investment. And so the Department of Energy is trying to help with all of that. X-Energy is a high-temperature gas reactor. They have a project with Dow Chemicals right now. So this is an industrial application. They're going to use heat and electricity. They're going to power some of their operations in Texas. And they use a special kind of fuel material called TRISO. And I'm going to get to that in a minute, what TRISO is. But they also have plans to be operational by 2030. The Kairos Power is a very interesting design. It combines molten salt coolant with TRISO fuel, and so they're actually in the process of getting approval for a construction permit from the NRC to build a small-scale test or pilot demonstration of this technology by 2027, and then they have plans for scaling their technology and being commercial in the 2030s with their technology. This is the key technology, TRISO fuel, that I wanted to mention. Now, not all advanced reactors are using TRISO. Some are, mostly high temperature gas reactors. Kairos is also using it. And the companies that have selected TRISO as their fuel have done it because of its safety characteristics. So TRISO fuel is uranium carbon molecules. So most fuel today, well, all fuel today for water-cooled reactors is uranium dioxide, so uranium oxide molecules. And so that uranium carbon forms very small particles, and those particles are encased in carbon, and we call those kernels. And then those kernels are all put together and encased in more carbon. And so what that produces is a very robust fuel form. It can reach very high temperatures, and so it's very difficult to, almost impossible to melt. If there were some mechanical forces on it, it would tend to break in chunks, and so it's much less of a hazard if that were to happen. And one of the unique things that they will be able to do, you're likely familiar, nuclear power plants have what are called containments, so that if we have an accident and the core melts and you get higher pressures, it's all contained. Well, for TRISO-fueled reactors, that fuel is going to be the containment because because of its so safety profile. So that'll help to improve the economics on the design of buildings and that sort of thing. Another key enabling technology is called a heat pipe. These are mainly used for microreactors, but not all microreactors use heat pipes. And if you're not familiar with a heat pipe, it's inside, it's porous, kind of like a sponge, and they basically suck heat from one place to another very, very rapidly. If you were to take a metal rod that's a solid metal and put it into something hot, it would take a very long time before your fingers at the other end get hot. But if you take a heat pipe with that porous sponge inside and you put it in something hot, instantaneously it would burn your fingers. That's how fast it can transfer heat. And so these are really exciting because now you can get away from the traditional ways of cooling reactors and transferring heat, which requires fluid flowing. Even if it's natural circulation, it requires fluid flowing. And now this just relies on that much more reliable heat pipe in there to transfer the heat very efficiently. One other interesting application that's starting to be discussed is our microreactors on ships. So the Russians actually have an SMR, very large SMR, on a barge that's in operation somewhere in Russia. And but there are other applications that people are looking at. The maritime industry has a lot of pressure to decarbonize their operations. Right now, diesel is about the only way to transport our goods across the sea. And so they're trying to figure out how they can do that. They're very interested in nuclear. Now, there's a lot of geopolitical, regulatory issues to work through by having a nuclear-powered transport ship go around the world. But certainly, we think the safety and the engineering could be worked out. So people are moving forward with that. Another key enabling technology is advanced manufacturing. The reason advanced manufacturing is excited is because a lot of nuclear's cost is in the construction. A lot of the cost in construction is related to time, but not just time, it's also in man hours. Advanced manufacturing offers the opportunity to reduce both the amount of labor hours that go into production as well as the amount of time that goes into production. So there are some examples of using advanced manufacturing already in the industry. Just an antidote of one application that's really exciting. So Oak Ridge National Laboratory has a lot of advanced manufacturing going on. I was there for a tour one time. And I looked over, and it was a Navy submersible, but it was about the same dimensions as a microreactor vessel. And come to find out that Navy submersible usually took tens of months to do and cost a lot of money. and they were able to do it in a matter of a few months and for like 10% of the cost. And looking at that, I thought, well, if we could replicate that for microreactor vessels, we could save a lot of cost on these and help to benefit even more. So it's just one example. And there's a lot of ways to it's not just 3D printing, there's other ways to do it as well. I want to talk a little bit about, so we talked a lot about the technologies and the opportunities. There are challenges ahead, and so the Department of Energy put together what they call an advanced reactor liftoff report. They actually have liftoff reports for many different types of technologies, and they outline both the opportunities, the challenges, and also potential solutions for moving forward. This is just one of the many graphs, and it shows a comparison of different technologies and their characteristics. But what's important is that the DOE is developing ideas on how to move advanced reactors forward and overcome the challenges of first-of-a-kind technology commercialization. The industry also did the same. We partnered with another industry association called Electric Power Research Institute. They do more of the R&D on behalf of the industry, where we do more of the advocacy. We also engaged other stakeholders in the process, and we developed what's called a roadmap. And the roadmap does the same thing. It looks at what are the opportunities, what are the challenges to get advanced reactors into the market, and then what are the potential solutions to overcome those challenges. And this is just one graphic from that. These are actually called the key enablers. And so the key enablers are those things that we need to solve in order to move forward. There are two, the first movers and fast followers. These are always a challenge for new technologies getting into the market. How do you get the first adopters to come forward and use that technology? Because almost always a first-of-a-kind technology is more expensive and higher risk than the lowest cost alternative in the market. The others, from regulatory efficiency all the way down to workforce, are more scaling issues. As we deploy possibly even 300 megawatts of new nuclear, or sorry, gigawatts of new nuclear, how would we be able to scale and do that? So this would really be addressing that artificial constraint that the VCE report built into one of their scenarios. There is a lot of policy support for advanced nuclear. So this is just three bills actually from Congress. There's the Infrastructure Bill, the Inflation Reduction Act, and then there's a CHIPS Act. Those all have support for advanced nuclear in them more recently. There's a lot of other bills that have been passed in the recent years, a lot of bills in front of Congress right now to support nuclear. Advanced nuclear is one of the only things that I know of that has broad bipartisan support in Congress. Not just Congress, but with the administrations, going back several administrations. And some support nuclear energy because it's zero carbon, others support because of national security, others support because of economics and jobs, others support it because it's reliable. But it has enough appeal to both Republicans and Democrats that both largely support it. And most of the nuclear support bills are unanimously passed. There is also now a lot of state action. This is actually really ramped up in the last 2 years. And we're also seeing at the state level a lot of bipartisan support. In the beginning, I actually did see some states where, if they're Republican or Democrat, they say, oh, if the opposing party likes nuclear, I must not like it because I'm an opposing party. And then they found out, no, they actually do like it. So now we get broad bipartisan support at the state level as well. And there's three main areas where their support is falling. One is removing barriers. There's some states that have moratoriums against building new nuclear. West Virginia is a recent example that they repealed the moratorium, and now there's a lot of talk in the state about bringing new nuclear advanced reactors to West Virginia. Another area is studies and commissions. So these would be states that look and say, well, we hear a lot of good things about advanced reactors. sounds like it could be for us, but we don't know. So let's go out and study it and find out what do advanced reactors mean for our state.
Hi. It seems like there's been a big increase in support for nuclear energy in the past. I remember in the past that nuclear energy was sort of seen as non-viable due to, I guess you can say, fictionalization in the media with stuff like Chernobyl and other energy crises.
Mm-hmm.
Do you think that the rise in government support is like mirroring public support and that disinformation or misinformation is starting to become clear, or do you think that's still going to be a big challenge before, like, for nuclear adoption?
Yeah, that's a great question and really well timed. So I do see that support for nuclear is increasing, not just politically, but also with the general public. And I think from what I've seen, the political support for nuclear actually was leading the public support for nuclear. And so I don't know if it influenced, but it was just in terms of time, it came before. What I'm seeing is that there's a lot of public support moving toward more nuclear energy. And I think it comes from three areas, and it's true for public support and for political support. And those three areas are this. First is that recognition of, or that question of, how are we going to decarbonize? That's the biggest challenge in front of us. And if we decarbonize, it has to be reliable and affordable, and that recognition that nuclear has to be part of the solution. So in terms of comparison, whatever people thought about nuclear energy, even if they had concerns over safety and waste, when they look at the challenges of climate change, they recognize, well, nuclear, whatever they thought about nuclear is much more agreeable than allowing climate change to continue. The second is in reliability, and a lot of this came after the Texas winter storm, which I guess was almost 2 years ago now. And it was that outage and the blackouts and the economic destruction that it caused that people started to realize, well, we have to not only decarbonize, it has to be reliable. And actually, we find in some places reliability is even more important to them than decarbonization. And so that's really important. The third is the Russian invasion of Ukraine. And so when people saw that, they said, well, energy security is really important, and where we get our energy and our fuel is really important. And so nuclear has always had a good nexus to supporting national security and energy security. And so for those three reasons, I think support for nuclear has grown. We see a lot of public opinion surveying, and a lot of it agrees that the general public supports nuclear to about 60 to 70% of the population actually is in favor of nuclear energy. But when they ask the question, does your neighbor support nuclear energy? The answer is 30% think that their neighbor supports nuclear energy. So one of the challenges is a perception, because we don't talk about it, because we may support nuclear energy, but we think the other person doesn't, so we're going to avoid a conversation because we just don't want the conflict. So I think there's a lot more conversation, and so those barriers are starting to break down. And then the other thing we've seen from a recent polling survey, this is from Potential Energy. They did a worldwide survey on nuclear energy, and what they found is that support for nuclear is independent of political affiliation, gender, race, anything like that. It's just sort of uniform, which is rare. Most issues have a breakdown, at least politically, are broken down by political affiliation, but not nuclear. And the other thing they found is that when you put factual information in front of people about used fuel, about safety, about other things, their support for nuclear increases. So yeah, I think talking about nuclear energy is the biggest solution we can for moving forward. Yeah.
Thank you for the presentation, Professor. So my question is regarding Nevada in particular. As we look to transition to clean energy, what do you think is the correct percentage of these various different sources of energy in your mind?
It's a good question. It's a really difficult question to answer. You can look at studies like VCE that project it, but these are, academics, so you have to take them for what they are. I think there's a few principles that will stand the test of time in thinking about the generation mix. The first is diversity. And so you don't want to put all your eggs in one basket. Just like in our investment strategies, we don't invest only in one thing. We invest in a couple of different things which don't have common risks, common susceptibility to the same risk. And so the same is true for energy generation, is you want a mixture so that that gives you the best reliability, the best long-term price stability, that sort of thing. The other is that it really depends on the specific location in terms of what is the demand profile and what is the other generation that's already on the grid, and to some extent, what does the transmission look like that connects all of that. So you'll find you could have two places that otherwise look the same, but because their current generation mix look different, or because their demand profiles look different, you might actually come out with a different optimal a situation. The third is that we need to start thinking more about not generation as its own decision, but you need to start looking at it as the total system and the total system cost. So it's generation and transmission and all of these things that are applicable. I think those three things would be so it doesn't answer your question, but it gives you a framework to work in. Yeah.
I'm glad you guys are all excited. It seems like we jumped right into questions.
Yeah.
I just want to make sure, is this your last slide?
I think I have two more, so let me go to that.
Let's hold on for further questions.
Yeah, thanks. So the third bucket is incentives, and there are states that are actually moving forward with incentives. Idaho has a tax incentive. There's other states that are looking at how do we incentivize nuclear energy to come to our state, and maybe not just generation. It could be the supply chain as well. When we look at near term, what are the likelihood of generation being built? We surveyed our members that own nuclear utilities. They represent only about 40% of the generation, and they said, this slide's a little out of date. Actually, it's 100 gigawatts. We reran the survey the next year, and they came back with 100 gigawatts. So already their plans for new nuclear is increasing. And if they represent about 40%, this trends well with the 200 gigawatts that we saw in those other studies. And they're also looking at operating the plants at least 80 years. This is a map. It's already out of date. This was from May, but it's tracking in green states that are taking actions to either have political policy support for nuclear, or there's other actions in the state to try to get new nuclear up and going. And the dots represent project locations that are being planned or considered for operation by 2030. And this is about 20 projects in North America. They represent a smattering of different types of application. There's a couple that are grid scale applications, like the one in Wyoming. There are actually microreactors to be used at universities, so University of Illinois, Penn State, Missouri, Purdue, Abilene Christian University. Many of those are looking, and universities have not just electricity needs, they also have heat needs for their activities, and high power needs. And so those universities are looking and saying, how can we replace our carbon emitting sources with clean sources? And they're saying, well, let's bring a nuclear reactor to our campus. And like University of Illinois, they're going to use it for heat and electricity and research purposes. And so actually when you turn it into a research reactor, things become a lot easier. So they're leading the way in trying to do that sort of thing.
What's the problem with Nevada?
What's the problem with Nevada? Well, I wouldn't say there's a problem in Nevada, but maybe you know better than I do. Yeah, this is the last slide, by the way, so we can go into questions.